Hello and welcome to our guide on finding the just right model in machine learning, a concept often referred to as the Goldilocks principle of data science. Training a successful machine learning model is all about striking a perfect balance. It shouldn't be too simple, but it also shouldn't be overly complicated. Our journey today focuses on taming the two biggest hurdles beginners face: underfitting and overfitting. We use the simple analogy of a bowl of porridge, or perhaps in this case, a bowl of soup, to illustrate these concepts. On the left, we have the too cold model, which is the state of underfitting. This model is too simplistic. It hasn't learned enough from the data to be useful. It's too simple to capture the underlying relationships. On the right, we have the too hot model, which is the state of overfitting. This model has learned too much. It's memorized the noise and random quirks of the training data, making it useless in the real world. Our ultimate goal, sitting perfectly in the middle, is the just right model or the optimal fit. This model is smart enough to capture the true patterns, but simple enough to ignore the random distractions. Over the next few minutes, we will explore these states, learn how to diagnose them using simple charts, and finally, look at two powerful solutions to ensure your model always lands in that sweet spot. Let's start by defining our overall objective. The big goal in machine learning isn't just to memorize answers, it's about achieving learning that lasts. We want our model to be truly smart, not just a good parrot. The fundamental challenge is transforming raw, noisy training data into a set of general, robust rules that hold true even for data the model has never encountered before. Look at the flow chart here. We feed in our training data, which in this example is a collection of various cat pictures. The brain of the model undergoes the learning process and ultimately spits out the rule. If this rule is too broad, say, all cats have 4 legs, it's too general to be useful for complex tasks like breed identification. That would lead to underfitting. Conversely, if the rule is too specific, for example, a cat is only a cat if it is gray-striped, sitting down and looking slightly to the left. It's useless because it's merely memorized specific images, not the concept of cat. That would lead to overfitting. The real test of success comes when we apply the rule to new, unseen data. The checkmark on the new cat indicates successful identification. The performance on this unseen data is what defines generalization. Generalization is the core objective of machine learning, building a model that performs well not just on the data it has already seen, but consistently and reliably on new, novel inputs in the real world. A model that generalizes is a model that lasts. To understand how models behave, we categorize their performance into these 3 distinct states. Let's look closer at the definitions. First, too cold, underfitting. The underfit model is severely lacking in complexity. It hasn't spent enough time learning, or perhaps it's constrained by being too simplistic to begin with. Think of it as drawing a straight line through a set of wildly curving data points. Its rules are extremely vague and simple. Critically, because it hasn't captured any meaningful relationship, it performs poorly on the data it was trained on, and it performs poorly on new, unseen data. It fails universally because it never learned anything useful to begin with. We often characterize underfit models as having high bias. Next, we have too hot, overfitting. This is where the model has learned the training data too well. It's become obsessed with every tiny fluctuation, every piece of noise, and every specific quirk of the training examples. It's essentially memorized the answer key. The consequence is that it performs fantastically, perhaps even perfectly, on the old data. However, as soon as you introduce new data, even data that follows the exact same underlying general trend, its performance collapses entirely. It fails because its rules are too specific to generalize. This state is characterized by high variance. Finally, the goal, just right, a good fit. This model finds the balance. It is complex enough to capture the general, underlying patterns and relationships in the data, but it remains simple enough to completely ignore the noise, the details, and the random errors. This is the model that generalizes effectively, performing well and reliably on both the data it has already processed and the new data it encounters in the wild. Our entire focus in training is guiding our model to this good fit. Let's dive into a practical example of underfitting using a scenario where we try to predict optimal background music tempo for a store based on the time of day. Imagine the owner prefers slow, relaxed music in the quiet morning hours and faster, upbeat music during the busy afternoon peak. The data points scattered on the graph represent the owner's actual tempo choices throughout the day. Our underfit model, shown here by the simple blue curve, is too vague. It's likely a very simple linear or low-degree polynomial model, meaning it has limited capacity to learn complexity. It's essentially drawing a simple, coarse arc through the data. Notice how this curve completely misses the important, subtle trends. It doesn't capture the dip in tempo immediately after the morning rush, nor does it perfectly align with the peak activity in the mid-afternoon. It's a passable guess, but it's too simple to be truly predictive. Because the model is too simple, it has failed to learn enough from the training data. If we were to use this model, the music tempo predictions would be consistently mediocre and likely frustrating for the store owner. This is the classic definition of underfitting. The model is incapable of detecting the signal because it is simply too vague and constrained. Now let's look at the opposite extreme. Too hot, a model that memorizes. An overfit model is often too complex and flexible, having far too many parameters, which allows it to stretch and bend until it hits every single data point perfectly. Look at the red curve on the graph. It's wiggly and erratic, attempting to pass directly through or extremely close to every single historical observation. While this curve achieves a near-perfect score on the historical data, the data it trained on, it is highly fragile. It has learned the noise, the specific, random daily fluctuations in the owner's choices, not the true, general preference pattern. The next day, when the owner makes slightly different choices, or when the data points shift even slightly, this ultra-specific rule becomes entirely distracting and useless. Its performance collapses on new data because it relies on those highly specific historical points. The analogy helps illustrate this point perfectly. If you meet a man named Walter with a walrus mustache and create the specific rule, walrus mustache equals Walter, you have achieved perfect accuracy for that single data point. But the moment you meet Bob, who also has a walrus mustache, your rule fails spectacularly. You learned the specific detail, the mustache, instead of the general characteristic of a person's identity. That is the essence of an overfit model: too specific, too noisy, and lacking in generalization. The goal, the true sweet spot we are striving for, is the just right model, a model that truly generalizes. This model avoids the pitfalls of both being too simple and being too complex. Looking at the golden curve on the graph, you can see it still captures the overall trend: the slower music in the morning, the ramp up towards the peak, and the slowdown towards closing time. Crucially, however, it remains smooth. It doesn't attempt to hit every single scattered data point like the overfit model did. It has intelligently filtered out the daily, random noise, the small fluctuations where the owner chose a slightly faster or slower song on a particular Tuesday morning, and instead focused on the consistent, general preference pattern. This model is complex enough to capture the real dynamics, but simple enough to maintain stability and robustness. It represents a good compromise between the simplicity of underfitting and the complexity of overfitting. If we deploy this model, we can trust that it will make accurate, predictable recommendations for music tempo on any given day, not just the days it was trained on. We want something that's not too precise a match or too loose, but just right. How do we move beyond analogies and actually spot these states of underfitting or overfitting in a real-world model? We don't guess. We use careful methodology to monitor our model's performance as it learns. The crucial first step is to correctly split our full dataset into two fundamental components. We must have data for the model to learn from and separate, sequestered data to test its generalization ability. First, we have the training data. This is the bulk of our data, typically 70% to 80% of the total. This is the data the model actively processes, analyzes, and uses to adjust its internal parameters and learn its rules. Second, we have the validation data. This is new data, typically 20% to 30% of the total, that the model has absolutely not seen during its training process. We use the validation data as an independent, unbiased judge. Its sole purpose is to check the model's generalization performance. If the model performs well on the training data, but fails on the validation data, we know we have an issue. By plotting the model's error rate on both sets of data simultaneously over the duration of training, we gain the key diagnostic tool needed to understand and manage our model's fit. The relationship between these two error curves is the definitive guide to determining whether our model is underfitting, overfitting, or achieving the perfect fit. This chart is arguably the most important visualization in managing model complexity, so let's take the time to read it carefully. It plots the error or loss of the model on the y-axis against the training time, measured in epochs on the x-axis. We are tracking two curves, the training error, the blue line, and the validation error, the red line. Initially, we are in the underfitting zone. As the model begins to learn, it improves rapidly. Both the training error and the validation error are high but steadily decreasing. This is a healthy phase, indicating that the model is actively learning valuable general patterns. The model is still getting smarter, and both its ability to perform on old data and generalize to new data are improving. As training continues, we reach the sweet spot. This moment occurs exactly when the validation error hits its absolute minimum point. This is the peak of the model's generalization ability. Up to this point, continued learning was beneficial. If we stopped here, we would have the optimal model. However, if we continue training beyond the sweet spot, we enter the overfitting zone. Notice what happens. The training error blue line continues to decrease, perhaps even approaching zero. This means the model is getting better and better at memorizing the training data. But at the same time, the validation error, red line, begins to rise sharply. This divergence is the telltale sign of overfitting. The model is sacrificing its ability to generalize in exchange for memorizing noise. The growing gap between the lines confirms that the model is becoming too complex and too specialized. Once we can accurately diagnose the state of our model using the error chart, we can apply solutions. The simplest and most fundamental solution is early stopping, and the principle is incredibly straightforward. When you observe the validation error begin to rise, stop training immediately. Early stopping is a powerful technique because it prevents the model from ever falling into the overfitting zone. We use the rising validation error as a tripwire. The validation set, which the model never sees during the actual learning step, serves as our impartial performance monitor. As long as the error on the validation data is decreasing, the model is still finding meaningful, general patterns. The moment that validation error starts to curve upwards, it signifies that the model is now focusing its energy on memorizing the noise in the training set, causing its ability to generalize to degrade. By implementing early stopping, we are essentially saying, the model has found the best possible representation of the data that maximizes its performance on unseen examples, so we will not allow it to learn any further complexity. It's helpful to think of it as last-minute stopping. We train for as long as possible, right up until the moment overfitting begins, ensuring we extract the maximum possible generalized knowledge without succumbing to memorization. Early stopping is great, but sometimes we need our models to train for longer epochs to capture very deep, intricate patterns. If we stop early, we might miss out on valuable learning, even if we avoid overfitting. This brings us to solution 2, change the recipe using a technique called regularization. Regularization allows us to train for longer while simultaneously preventing the model from becoming excessively complex. It's a mechanism that forces the model to prioritize simplicity and smoothness, even if that means achieving slightly less than perfect performance on the training data. The analogy here is perfect. Think of cooking a turkey. If you blast it on high-heat model without intervention, the outside burns, overfitting, before the inside is properly cooked, deep learning. Regularization is like wrapping the turkey in aluminum foil. The foil, which is the constraint we introduce, delays the burning process, allowing the inside to cook thoroughly. In machine learning terms, regularization methods introduce a penalty to the model's cost function proportional to the magnitude of the model's parameters. By penalizing large parameters, we encourage the model to keep its rules smoother and less extreme. This mechanism effectively delays the onset of overfitting, allowing the model to safely learn more from the data without resorting to memorization, ultimately leading to a better, more robust model. To understand how regularization works, we need to focus on what happens to the model's internal dials or parameters. When a model overfits, it often relies extremely heavily on one or two specific features, assigning massive weight to those features to perfectly match the training data. This is how the walrus mustache equals Walter rule gets created. The core idea of regularization is to put a leash on your model by limiting the values of its parameters, forcing them to remain relatively small. Look at the sliders. Before regularization, one feature, mustache, is cranked up to 100%, dominating the decision. The other features, height, shirt, and voice, are barely considered. After applying regularization, indicated by the add regularization lambda symbol, the model is penalized for having that 100% weight. It's forced to distribute the predictive power more evenly. Now, mustache is still important, but its weight is reduced, and the model must rely moderately on height, shirt, and voice as well. This makes the rule much more robust. This distribution prevents any single feature from dominating the decision-making process. The result is a simpler, smoother curve that ignores noise. The control knob for this entire process is a hyperparameter called lambda. We tune lambda ourselves. A higher lambda value means we are applying a stronger penalty, forcing the model to be simpler and smoother, thus providing more regularization. To truly master the just right model, we must turn to the underlying theory, the bias-variance trade-off. These concepts are the theoretical backbone of underfitting and overfitting, helping us describe the fundamental tendencies of any model. Think of these as two different types of error your model can make. First, we have bias. Bias is the systematic tendency for a model to consistently learn the wrong thing. It represents the error introduced by approximating a real-world problem, which may be complicated with a simplified model. If a model is severely biased, high bias, it is too constrained. It cannot capture the complexity of the data, regardless of how much data you feed it. High bias is synonymous with underfitting. We often think of bias as prejudice. The model has a strong, simple idea that consistently misses the mark. Second, we have variance. Variance is the tendency for a model to learn irrelevant details or noise. It describes how much the model's predictions would change if we trained it on a slightly different training set. If a model has high variance, it is overly sensitive to small fluctuations and outliers in the training data. High variance is synonymous with overfitting. We can think of variance as sensitivity to noise. The model is wildly inconsistent, changing its rules drastically based on minor changes in the input data. Understanding how to manage these two opposing forces is the key to successful modeling. This visualization perfectly illustrates the difference between high bias and high variance models. Imagine we run an experiment where we take the same underlying data, create 50 slightly different subsets by adding minor noise, and then train 50 individual models on these subsets. On the left, we have the high bias/low variance, underfitting, family. We deliberately constrain these models to be very simple, perhaps using only a first or second degree polynomial. Because they are structurally simple, the 50 resulting curves are all highly similar to each other. They have low variance. They are predictable and stable. However, they consistently miss the complex wave pattern of the data, meaning they all share a strong bias toward being simple, resulting in poor fit overall. They are reliably wrong. On the right, we have the low bias/high variance overfitting family. We allowed these models to be extremely complex, using high-degree polynomials or deep networks. Each curve contorts itself perfectly to fit its specific data points. They have low bias because they accurately map the training data. However, the curves are wildly different from one another. They vary a lot. A small change in the training data leads to a drastically different resulting curve. This high variance means the model, while accurate on its training set, is wildly unstable and unreliable when encountering new data. This brings us to the crucial concept that dictates all model building, the inescapable trade-off. In virtually all real-world machine learning scenarios, bias and variance are inversely related. They operate on a seesaw principle. As you decrease bias, you increase complexity, which invariably drives variance up. Conversely, as you try to reduce variance by simplifying the model, you increase the approximation error, thus driving bias up. It is impossible to achieve a model with both zero bias, perfectly fitting the trend, and zero variance, perfectly stable across different datasets. That unicorn model simply does not exist. The seesaw visualization helps us understand this balance. Simple models rest on the side of bias, which is the heavy weight that risks underfitting. Complex models rest on the side of variance, which is the messy, tangled weight that risks overfitting. Your job as a data scientist is not to eliminate these risks, but to manage them. The ultimate goal is to find the sweet spot, the pivot point on the seesaw where you have achieved the optimal bias-variance trade-off for your specific problem. This is the heart of engineering a just right model that achieves maximum generalization ability in the real world. To wrap up our journey, let's summarize your Goldilocks toolkit for building better models. When you are developing or troubleshooting a model, you should follow these 3 steps. Recognize the problem, diagnose it with the chart, and apply the appropriate solution. The problems: if your model is too cold, you have underfitting. Your model is too simple and its performance is poor everywhere. If your model is too hot, you have overfitting. Your model is memorizing noise, resulting in great training performance but terrible generalization. The diagnosis: the key diagnostic tool is plotting your errors. Watch the training error and the validation error over time. The telltale sign of overfitting is when the validation error starts rising while the training error continues to fall. That divergence is your cue to intervene. The solutions: we have 2 powerful techniques to manage the fit. 1. Early stopping. This is a timing solution. It means stopping the training process right at the moment the validation error hits its minimum, the sweet spot, to prevent the model from entering the overfitting zone. 2. Regularization. This is a recipe solution. It means applying constraints, via lambda, to the model's parameters to prevent it from becoming overly complex or reliant on single features. Regularization allows you to train for longer, increasing the model's capacity to learn deep patterns while simultaneously preventing it from learning irrelevant noise. By utilizing these tools, you can ensure your models consistently generalize effectively and achieve that perfect, just right fit.